when you're holding a wheel, driving a car, when you are tightening a big valve, let's say in a power plant, I would say, or somewhere that like industrial environment, you will see these kind of valves. Very common example is when you are changing the tire of your car and you're using some kind of a long wrench. What happens is that typically you're applying two forces in opposite directions with the same magnitude. So that's a special case that needs more attention. I'll put it under moment of a couple. This is called couple. The definition of couple is two forces that they have the same magnitude and they act in opposite directions. So let's put it under moment of a couple. Well, we have to start with the definition of couple. So couple, as I said, is we can define it as two forces that are parallel. They have the same magnitude, but opposite directions. And from what you see in these examples, they are separated by some perpendicular distance, right? There's a distance between these forces, obviously. So let me put it in words. A couple, hopefully I'm so close to definition in the book, is defined as two parallel forces that have the same magnitude and opposite directions. Opposite directions. We can also add that they're usually separated by a perpendicular distance d. Right? Here we have this distance between these two, perpendicular distance. This is d. In this case, this perpendicular distance is d, and in this case, this is d. Now, obviously, looking at this, we can easily see that the resultant force is zero. We have two forces acting in opposite direction with the same magnitude. So summation of forces is equal to zero. But what happens is that we still are going to have the moment. So this couple is going to create a moment, which is what we're going to talk about, moment of a couple. Right? Now, if it's possible and if there is enough force, we are going to have, we're going to produce, right, a kind of rotation. We're going to have a rotation in that system, depending on how strong the forces are and whether they can overcome the resistance we have in that system. So they have the tendency to produce a rotation. But there is no motion, I would say, because the summation of forces is zero. So let's use what we've learned from before to find out what is the moment of a couple. Right? If I have a force, let's say in this direction, let me do it the other way. If I have a force in this direction, another one parallel to this force, same magnitude here. So I call this F, I call this minus F. It's two forces to have the same magnitude. And I want to find the moment of these two forces. It's a system of forces around point O. So I'll find the vectors. I find this one, let's say, and let's say this one. I'll call this one R. Let's name this point A and name this point B. I call this one RA and this one RB. Remember, we said as long as the points that we, or better to say the position vector going from the point we want to find the moment about is on any point on the force, we are good to go, right? I said I usually go with the beginning or the end of the force vector, but it can be anywhere along the force vector. So I just put it somewhere in the middle, A and B. But A and B are points on these two force vectors. So from what we know from before, we know the moment about point O as a vector would be RA times FA, right? Position vector times force vector, plus RB times FB. We already know this. FA and FB, I could just replace it there. I just put FA and FB, but what I did and I put in the figure is times F plus RB times minus F. It's just the magnitude. Just put it this way. Now, if I just factor out F, what I'll get is MO is RB minus R, or let's put it this way. Yeah, let's put it this way. It becomes RA minus RB times F. These are vectors. Now, look at what we have there, right? RA and RB, pretty much the difference between these two would be R. I'll put it, try to draw it in a good way. Let's define R this way. Let's see what happens. I'll define R as this. So hopefully you remember from vectors that these are vectors. Everything is a vector here. So let me make sure that we have the arrows there. So can someone tell me what is the sum of these three vectors? We have RB, RA, and R. How do you write the summation here? All the way back when we were talking about triangle rule, I would say. So look at this triangle, this RB, R, and RA. Can I say RB plus R is equal to RA? Can I do that? Just say yay or nay, something that I know it makes sense to you. Okay, yes, yes, good. Okay, so we agree on that from what we know from vector operations. So what happens is that, well, R is equal to RA minus RB. That I get from here. So I can easily write this as MO is equal to R cross F. Now look what I got. What does this tell me? This is the equation for the moment that is created by this couple. The interesting thing in this equation is that now this moment is independent from RA and RB. It only depends on R. And what is R? R is the distance between A and B. Oh, sorry, is a distance, well, it is a distance between A and B, or the distance or perpendicular distance between vectors F and minus F. So if I have a couple, two forces parallel, same magnitude, opposite direction, the moment that couple creates is a free vector, meaning that it can be anywhere in the space, because I don't care anymore about the position vectors RA and RB. The moment it creates about point O is the moment it creates Generally, doesn't matter which point I'm looking at. Interesting, right? So it's a free vector, can be anywhere. Its position, the position of this couple, as long as these two forces move together wherever they go, the position of this couple does not matter with respect to some point, does not matter. What matters is the position of these two forces with respect to each other. As long as they're parallel and the distance is the same, the couple, the moment of the couple is the same. So it can go anywhere in this space. So I can even get rid of this O there, and I say this is just the moment of this couple. It has nothing to do with the point I'm finding the moment about. So let me just write it here. So M, to emphasize, is a, I would call it a free vector. Rotation. It can act at any point. It only depends on F and the distance between those two forces. Now, since M is a vector, remember we said whenever we talk about the vector, two things are the immediate things that should come to your mind: magnitude, direction. So we need to know its magnitude, we need to know its direction. Right? We just wrote it as general form as a cross product, right, in 3D space. Now, if you think about it, right, let's write it this way. So I have my M moment as the cross product of R and F. R being the distance between two vectors or two forces, and F being the magnitude of the force. Well, the vector force, depending on which direction you get, positive or negative, that doesn't matter.
Professor, can you go back to the last slide for a second?
Sure.
Just real quick.
Mm-hmm. So we started from system of forces, of course. System of forces, we already knew about system of forces, how to find the moment for a system of forces. Now we're looking at a special case, a couple. System of forces that are two forces that are parallel, same magnitude in opposite direction. Now, since it is a vector, right, set, it's going to have a magnitude, it's going to have a direction. That's how we deal with vectors. We need to know these two things. Now, in terms of magnitude, right, I can say M, the magnitude of this. I don't put the absolute value around it, but you know, just it's a magnitude since I'm not putting the vector sign. Is FD. D being the distance between two forces, right? If I draw it here, and if this is one force and this is another force, of the same magnitude, so same length. This would be the distance D, and F is the value or the vector. Could be one is positive, one is negative, depending on which direction you take as positive and negative. Now, in terms of direction, we define or we determine the direction using right-hand rule. So let me put it this way: determined by the right-hand rule. What do I mean by that? So if the same story, right? If my four fingers represent the direction of one of these forces, right? It doesn't matter which one, that one or this one. As long as the palm of my hand is facing the point that I'm finding the moment about, right? The moment is created, in this case, you can think about the point exactly between these two forces, middle point. You can think about that as the point. This, and if I make a fist, right? In this case, let's say this is the direction, the palm of my hand towards the middle point between these two forces. If I make a fist, right, in 2 dimensions, the direction that my fingers are going, right, 4 fingers are going, is the direction of the moment, either clockwise or counterclockwise. 3-dimensional space, you can think about the direction of my thumb as the direction.
51.
So let me bring this picture. This might make it clear a little bit. So 4 fingers, the palm of your hand, facing the point, some point between these 2 forces. Make your fist. The direction of your fingers show the direction of the moment in 2-dimensional space. Your thumb shows the direction of the moment vector in 3-dimensional space. Depending on which one you want to go with the vector representation and do the cross product, or you want to just do it in 2D plane and don't deal with cross product operation, as long as you take counterclockwise as positive and clockwise as negative. So now hopefully we understand the concept. This is the concept of the moment of a couple. We have a couple, that couple creates a moment. That moment is independent of its the forces, positions with respect to a point. It's a free vector, it can go anywhere. We can find its magnitude and its direction as long as we know these 2 forces, and their directions and their values, and we know the distance between these 2 forces. All right. Now, natural step after this, that's what we always do. How can we find the resultant of the moment? What if we have so many of these moments in or problem, engineering problem we are trying to deal with? Or what if we have so many or multiple couples? Right? Each couple is going to create a moment, and then how can we find the resultant of that moment or those moments? So, quick note. You already know that, you've seen it multiple times, but let me put it on the, so resultant of the moment. Write it this way. Moments, let's put it this way, moments are vectors, so their resultant can be found by vector addition. What do I mean by that? Well, resultant of moment, resultant of the moments, multiple moments, pretty much is the summation of all those moments. Right? Say I from 1 to n, multiple moments. You can expand this and say, well, I from 1 to n, right? And in this case would be Ri times Fi. Keep in mind, this R is the distance. This is the distance between the couples, right? Between couple Fi. If you have two forces, this R is that distance. It's different from that R1, R2, Ra, or Rb that they were pretty much the position vector. It would have been easier if the book was using Di instead of Ri, but that's what it used, so we'll follow that. To visualize this, I can also use an image from, these are, I think, are not from your textbook. It's from the other textbook I put in the syllabus, Hibler, but I use figures and examples from both. So here's an example. If I have M1 and M2, example of 2 moments. It's a moment vector. It has some direction in 3D space. M1 and M2, we'll just do the vector addition. You can find MR. If you want to visualize this, how it works in 3D space.